questions. So today we're starting chapter 13. We're going to talk about solutions. If you printed out the slides, I'm sorry, I did change them a little bit today to hopefully make them more efficient and to change the flow just a little bit. So I added this overview slide. These are like the key questions that we're going to be answering throughout this chapter. We'll probably get up to molarity today, actually, because most of this is conceptual stuff. So talking about what solutions actually are, and usually we slow down when we start getting to actual problems that we work out. So we're going to talk about what are solutions, what are electrolytes, what is a saturated solution, what is recrystallization, can gas-liquid solutions be saturated, and then units of concentration. So we'll talk about mass percent, molarity, dilution. There will be some stoichiometry involved with solutions. And then we'll finish off with molality and then briefly mention osmosis. So solutions, what's in your water? So pretty much everything that we interact with, everywhere, every day, is a solution of some kind. Whether it's a gas dissolved in a gas, or gases mixed, like air is a solution of different gases, or if it's your water, which is a solution of minerals mixed into that water. So, one of the, I consider it one of the greatest crimes of the 21st century is that Coca-Cola, actually not even the 20th century, is that companies like Coca-Cola and Pepsi take tap water, they purify it so that there's nothing in it, and then they re-add minerals like magnesium sulfate, potassium chloride, and salt. So this is why every bottle of Dasani tastes the same, because they add the same amount of minerals back into it. And actually, if you tried pure tap water, you probably wouldn't, or sorry, not pure tap water, pure water, you probably wouldn't like it, because it wouldn't have any flavor at all. Even less than like the purifiers that you have at home, because those don't even get everything. Pretty much everything has some amount of sodium on it. So everything's a solution. Not all of our solutions that we encounter are homogeneous. So usually water is a homogeneous mixture, meaning that those two substances are mixed with an even concentration throughout. So you could sample any part of a Dasani water bottle and you'll get the same measurement of magnesium sulfate, potassium chlorate, and salt, which here is sodium chloride. So there is a table in your book that lists the different types of solutions that you can have. A solution may be composed of a gas and a liquid and another liquid, a solid and a gas, or other combinations. One of the interesting ones, I think, actually is solid-solid solutions. So alloys are mixtures of two different metals in specific ratios. So anything like the metal that makes up most of your car, I think is it an alloy? It might be pure aluminum. It's probably an alloy of some kind. So two different types of metals mixed together or other solids. So you can look through that list. So we have technical terms for describing a solution. It's not just the thing dissolved in water and water. The solvent is the thing that is the majority component. So most of the time we think of stuff dissolved in water, water is that majority component, and then there's other small amounts of things mixed into that. Those other small amounts are solutes. So each solute is the minority component, and so you could have more than one type of solute. For the most part, when we talk about solutions, we're going to be talking about solids dissolved in liquids. And usually, the liquid is considered the solvent. And most of the time, there's more liquid than there is solid. There are special situations where you can dissolve more solid than there is liquid, particularly fructose, which high fructose corn syrup, which is in sodas. They use fructose in soda because there's so much sugar, table sugar would not be soluble. So you could not dissolve as much table sugar as you can fructose in water. That's why sodas can have so much sugar in them. And we also talked about the name of these solutions with water, they're aqueous solutions. So if we had in a chemical equation, NaCl with this parentheses AQ, that parentheses AQ means aqueous, or that it's dissolved in water. Other solvents are also used, especially to form solutions with nonpolar solutes, and we'll talk more about those later. Or I guess we're talking about them now. So like dissolves like. So we have basically two types of solvents. We have polar solvents, and we have nonpolar solvents. This definition of polar, I know this is going way back to before spring break and even before last week, but when we were talking about Lewis dot structures and whether something is polar or not, that's the exact same definition that we're using here. So these things have one side that's positively charged, one side that's negatively charged. Those are our polar solvents. Nonpolar solvents are things that don't have a distinguishable charge on one end or the other. So like dissolves like. If you have a polar solvent, it will dissolve polar things. If you have a nonpolar solvent, it will dissolve nonpolar things. They will not dissolve the opposite. This is why we need dish soap for washing dishes, because grease is a nonpolar solid or semi-solid sometimes, and water is polar. And I think I mentioned this briefly when we were talking about intermolecular forces. Those are coming into play here again. The strength of the intermolecular forces between the water in this case and the sodium of the sodium chloride, and again, this is the negative end of the water with the positive charge on the sodium, the positive end of water with the negative charge on chlorine. If these interactions, these intermolecular forces between the water and the chlorine, or the water and the sodium, are stronger than the the sodium and the chlorine holding themselves together, then it will dissolve. It's kind of like a tug of war. So if water wins that tug of war, then the thing dissolves. If it doesn't, that thing stays stuck to itself, which is why calcium carbonate is not soluble in water, because the calcium wants to stick to the carbonate more than the water wants to stick to the calcium or the water to the carbonate. So it's like this tug of war. Again, so the water is trying to pull the sodium away from the chlorine, but the chlorine is trying to hold on to that sodium. In the case of sodium chloride, this is a stronger intermolecular force. And so because that force is stronger, it will dissolve the sodium chloride crystal. For anything that's weaker, it won't dissolve. And so we've talked about these up until this point. We don't know what these exact strengths of these intermolecular forces are. We could infer them because we have a solubility table that we got way back in probably chapter 7, chapter 8, when we were talking about chemical equation or chemical reactions. But those just kind of told us this does dissolve or this does not dissolve in water. So what happens is when these ionic compounds in particular, dissolve, you get the water molecules surrounding the chlorine and the water molecules surrounding the sodium, or whatever ions might be present, and keeping them from getting to each other. So if they can never get to each other, they can't stick back together because there's so much water that creates a literal bubble around them. So when we do get these ionic compounds that dissolve, these chlorine and these sodium ions, so this is why you could write this out as sodium chloride goes to Na plus Cl minus. If you remember net ionic equations, these ions get separated in this solution. So this chlorine becomes just another isolated chlorine, and the sodium becomes an isolated sodium. This will become important again later, but we have to talk about concentration first. Keep this in mind though. Ionic compounds dissociate into their individual ions. So our solubility rules gave us a qualitative description. They told us, yes, this thing will dissolve. No, this thing will not dissolve. And we have some ionic compounds like calcium carbonate, which are insoluble, again, because the attraction, or the intermolecular force, between the ions and the water is greater than the solute. Or sorry. The intermolecular force between the ions is greater than the force between the water and the solute. So here this will be the water, and this would be the calcium carbonate. And then we also have, so those are ionic compounds for molecular solids. Those will also be soluble depending on if the solvent is polar or not, or the solute is polar or not. So table sugar is polar, and it's soluble in water. But as I was mentioning earlier, nonpolar solids like lard or vegetable shortening or vegetable oil or butter, those are insoluble in water because they are nonpolar molecules. Okay, so that was that solubility table was the qualitative. It just kind of gave us yes or no answers for if things were soluble. But we can quantify actually how much of a soluble compound will go into a solution. So we call this the solubility of a solid in a liquid. It can be defined exactly as the mass of the solid that can be dissolved in a mass of water, or mass of the liquid. So in this case, the question I want to answer is how many grams of salt could dissolve in 100 grams of water? So, actually I meant to put this in there, but if we go back to this picture, right, it takes way more water molecules, because this is not just surrounding this in a circle, but like I said, this is a bubble. So there's like water molecules that are in front, and there are water molecules behind. And it takes all of those water molecules to keep the sodium and the chloride apart. So at some point, if you add enough salt, there will be too many sodiums and chlorines for the waters to surround. And then those things will no longer be soluble, and you'll have extra salt that does not dissolve. So there's a saturation point where you've used up all of the water molecules. Right? So at some point, there won't be any water molecules left to pull apart the sodiums and the chlorines. So that's what happens when you add too much of something to water and it doesn't dissolve. That's somewhat dependent on temperature. So we're not going to be calculating the solubility of anything. We'll mostly be using experimentally determined numbers. And we'll look at a graph, but you usually see these presented in a table or a graph. For sodium chloride, temperature is important, but you can dissolve 36 grams of salt, sodium chloride, in 100 grams of water. If you add any more salt than that, it won't dissolve, and it'll just sit on the bottom. So at that point, you've made a saturated solution. So a saturated solution holds the maximum amount of the solute under the solution conditions. So mostly the solution condition for this class will be just the temperature of your solution. And again, if we add more salt to that saturated solution, it will not dissolve. It'll just sit at the bottom. So we can also have undersaturated solutions, or unsaturated, and that's just any solution that is less than the maximum amount. So for less than the maximum, that's an unsaturated solution. Most of the solutions we work with are unsaturated. You can, under special circumstances, get a supersaturated solution, which holds more than the normal maximum of that solute. These are really unstable, so usually even just bumping it will cause it to precipitate out of the solution. One example would be it's like a soda can where you have it under high pressure. That allows more of the carbon dioxide to be dissolved in the soda. Oh, I forgot to pull these up. So, cool example of a supersaturated solution is sodium acetate. Let's just open this up, see if it works. Hopefully the sound's not on. Oh. Why did that stop working? What? All right. Let me try something else. Oh, that really broke it. Technical difficulties. Nope. All right, well, I guess we're not going to watch that. It's just so unhappy with whatever it did. Okay. So maybe we can try it. Okay. Nope, and then it just gives up. Okay. Bummer. Okay, well, with sodium acetate, there's just a picture here. So you can look at the sodium acetate. That's a supersaturated solution. If you add, and they're doing this with this glass stir right here, a single crystal, it instantly crystallizes and will fill up the whole thing. You can also take it, I don't know if you've ever done this with wet sand on the beach, but you can take the sodium acetate and you can pour it, and as soon as it hits whatever you're pouring it on, it will turn into a solid. So you can pour little towers of it. You can do that with wet sand on the beach. But the video's not working. All right, so that's a supersaturated solutions. You can get those to crash out. So now we're coming back to our the idea that when we have dissolved ions, such as sodium chloride, right, we have these separated charged ions in the solution. This is called an electrolyte solution, which contains dissolved ions, which are charged particles, right? So each sodium has a +1, each chlorine has a -1. Non-electrolyte solutions are solutions of molecular solids, usually, which are neutral particles. So if you're to look at any one of these sugar molecules, it doesn't have an overall charge. So this electrolyte solution, you could actually stick two ends of a wire in it, and it will conduct electricity. This is why the experiment that I've mentioned probably several times now, where you put a 9-volt battery in salt water, it has to be salt water because it's conducting electricity through the water and also separating the water into hydrogen and oxygen. But it won't do that with a sugar solution. You'll just have a sticky 9-volt battery, which is not as much fun. So electrolyte solutions come from charged particles. Non-electrolyte solution come from neutral particles. So as I mentioned, the conditions of a solution determine how much can be dissolved in that solution. So if we increase the temperature, so solubility increases with increasing temperature. So you can dissolve more things, generally because there's more energy to dissolve them. So sugar dissolves more easily in hot tea than it does in iced tea. or coffee or anything. This is why if you've ever made simple syrup, you dissolve a lot of sugar in hot water because it dissolves way faster than if you do it in cold water. So the temperature dependence of solubility varies depending on the compound. So here we've got solubility, so that's how many grams of the solute, and each of these lines represents a different solute. It's how much you can dissolve in 100 grams of water. And then on the x-axis here, we have the temperature. So you can see for all of these, the solubility goes up. So solubility is going up as our temperature goes up. And so we can use this and determine if things are going to be soluble at various temperatures. Oh, I forgot to set this up. So I did set up a Multimeter Quiz thing for this. So let me hit present on that. Go back over to here. Pull up this. So the code for the Multimeter Quiz, if you remember, I'm going to do it this way. Because you're going to need the slide for this. 5570-0694. So I just wrote that on the slide for you there. I'll write it up here at the top too. Okay. So we're going to work on this first one, is the Multimeter Quiz that I have pulled up. So if we have 50 grams of potassium chloride, so this line is potassium chloride, in water at 50 degrees C. So if we go to 50 degrees C and we go up to 50 grams, so that would be right here. This line is representing where our solution would be saturated. So for potassium chloride, that means that just above 40 grams, if you look over right to the left side here, right, that's just over 40. So that would be saturated. So if we're above this line, that means it's a supersaturated solution. So on the Multimeter Quiz, should be voting whether it's unsaturated or supersaturated. So if we're above the line, it's supersaturated. That is where the majority of the votes are coming in. So that's really how you do these kinds of problems. Moving on to our next one, if we have 10 grams, we'll delete these, 10 grams of potassium chlorate in 100 grams of water at 70 degrees C. Is it going to be unsaturated or supersaturated? So the way you read these is you either start at the x-axis or the y-axis. You start at the temperature, or you can start at the mass. You can draw a line over, you can draw a line down. So 10 is here. So it's below the line. Simple enough. Looks like we had one vote for supersaturated. So it's under the line for potassium chlorate. That means that we are, so this is the line for potassium chlorate. So it's unsaturated. All right. Moving on to the next one here. If we have 40 grams of sodium chloride in 100 grams of water at 30 degrees C, it's going to be unsaturated or supersaturated. $40 grams at 30. So again, you got to make sure you know which line you're looking at. You got like 14 votes in here, so that's most of them. So we're at 30 degrees C, and we're looking at the sodium chloride line. So sodium chloride's there, so it's this green line. And if we have 40 grams, that means we go all the way up to here. So it's over the line, supersaturated. All right. So those are simple enough when you're given the number in terms of 100 grams of water. Right? So this is on our chart per 100 grams of water. So if it's anything other than that, like this next question here, then we have to sort of change the numbers to say, okay, what if this was 100 grams of water? So for this one, because we have 25 grams in 50 grams of water, to get what we would have in 100 grams of water, we have to double both numbers. So if this is, I'll write it this way, 25 grams of KCl over 50 grams of H2O. Right, so 50 is half of 100 grams of water. So we'll double the amount of water. But if we double that, we have to double our amount of KCl as well. So we multiply that by 2 also. So instead of 25 grams in 50 grams of water, if we had 100 grams of water, it would be 50 grams of KCl in 100 grams of H2O. Now we can use that, because it's in the same units as our graph, and go look at 90 degrees C, and go up to 50 grams of KCl, which is right here. So that one would be undersaturated. All right, the last one of these then, let me erase this too. So if we have 90 grams of potassium nitrate in 200 grams of water, how many grams of potassium nitrate would we have in 100 grams of water? 45. So again, we just need to sort of translate this into what it would be at 100 grams of water. Because it doesn't matter actually, the numbers actually only matter as a proportion. So it's how much solute, in this case potassium nitrate, you have per gram of water. But 100 grams is easier to work with, so we just use 100 grams. So if we take the 90, grams of KNO3, and 200 grams H2O. We have to divide 200 by 2 to get it to 100. So we also divide the 90 by 2. Whoops. So we'll get 45 grams of potassium nitrate per 100 grams of water. Potassium nitrate is this line. So is that going to be undersaturated or unsaturated or supersaturated? Yeah, unsaturated. Because it's 90, yeah, 40. So if we're at 40, then we go up to 45, it's below the line. So you've got to make sure when you're working with a graph like this that your amount of water matches the amount of water used in the graph, which is almost always 100 grams of water. All right. Are there any questions about that? Well, one more question we're going to do with relation to these. No? The hardest part of these is always going to be just kind of translating it so that it's the same as the graph. And then you just find that point on the graph. And if it's below the line, unsaturated. If it's above the line, it's supersaturated. And the one that I didn't have a question here for was, mostly because of the way the slides are, if it's on the line, then it's just saturated. So if somebody said, well, actually, we'll get to that in a second. So we can use this fact that things are more soluble at high temperatures to actually purify solids if you're doing some sort of organic chemistry or if you're just trying to purify something. What you do is you make a saturated solution of a solid at an elevated temperature. Then you let the solution slowly cool. Oh, and I had another video here that's not going to work. So you let the solution slowly cool. I think you can find it while I talk about this. And as it slowly cools, that crystal will begin to form. And as it forms, seriously? As that crystal begins to form, it will exclude or leave out anything that shouldn't be part of the crystal. And there's a very particular memory that I have from the Magic School Bus that I remember about this. And I found it. Oh, here we go. So this recrystallization process is very useful for purifications. It's also useful if you wanted to make rock candy. Oh, we'll give this example first. Nice, I think that'll work. Okay, so with recrystallization problems, they'll look a lot like this. You'll get something like a saturated solution of potassium nitrate in 100 grams of water at 50 degrees C is cooled to 20 degrees C. How many grams of potassium nitrate crystallizes? So first thing, how much potassium nitrate is in a saturated solution at 50 degrees C? So what we do is we go over to our graph and we find 50 degrees. And then we look all the way up to our potassium nitrate line. So that's just under 90 grams. We'll call it 88 grams. So we have 88 grams of KNO3 in 100 grams H2O at 50 degrees C. So if we cool that solution, oh, yeah?
How do you know it's 88 grams? So are you looking for like on the, so you're looking for the KNO3, right?
Uh-huh.
That line, and so you're trying to, are you approximating, or are you?
I'm kind of approximating here, so, because you would draw this line across there.
Wherever it's kind of perfect, right?
Yeah, so where the potassium nitrate line, green line, let me zoom in on this, is crossing that vertical line that's 50 degrees C. Okay. So that line is 50 C. So wherever those two lines cross, then you look over to the y-axis, so here, and then because it's a graph, because we only have 80 to 90, or we only have the numbers 80 and 90, then we approximate, that's like 88, maybe you call it 89, maybe you call it 87. So there would be some approximation there. But you couldn't approximate any farther than the ones place because all we have is the tens place. On an exam, I would usually pick one of these lines that crosses more nicely at an intersection. What I mean by that is, oh, like here. So like here, potassium nitrate at 10 degrees C crosses pretty much perfectly with 20. So you would just call that 20. Yeah, so we're approximating this here. So that's how much can be in there at 50 degrees C. And we're told that we have a saturated solution. So there's that much potassium nitrate in our 100 grams of water. If that's cooled then to 20 degrees C, so 20 degrees C, that does cross nicely on this line. The maximum that can be dissolved in 100 grams of water at 20 degrees C is only 30 grams. So saturated, 30 grams of potassium nitrate in 100 grams of water at, what was it, 20 degrees C. So the difference in those is what crystallizes. So if we're starting with a solution with this much potassium nitrate, and we cool it down, assuming that it crystallizes, then when we get to 20 degrees C, only 30 grams can be left dissolved. So 88 minus 30 will give us 58 grams of potassium nitrate crystallized. So you're just finding the difference in one point to another. So any questions on that one? No? Okay. Yeah, so you can also use this to make rock candy. Be forewarned, if you go home and you want to make rock candy, it does take like 3 or 4 days for it to crystallize. I tried to do this for my nephew when he was here for a week, didn't realize that, and then we never got to eat rock candy. Or he didn't, I did. And you need, like, don't use too much water because you need a ton of sugar because it's very soluble. And use a lot of food coloring if you want it to be different colors. So, yeah. And actually, don't use strings. Use like disposable chopsticks. Because a string, you have to like tie something to the end of it to hold it down. Otherwise, it'll float. But what you're doing here is you're creating this supersaturated solution. Well, not even a supersaturated solution, a saturated solution. So this is like, we assume that this potassium nitrate was sugar. We're creating this solution that has a lot of dissolved sugar, and then we're cooling it down. And as it cools down, that's no longer soluble, and it starts to form crystals. Again, in particular, I did pull this up. So Magic School Bus, I remember this from just way back. There's not going to be any sound, apparently. I think, oh wait, 918. The dilemma that they've all shrunk down to the size of the molecules, right? And the dilemma here is that they broke the hood ornament on this car. And so they're going to make a new one out of sugar. But what I thought was really cool, and I remembered from this, I went farther back than I wanted to. So, right, they're all around. The molecules don't really look like this, but close enough. So they're trying to stack these one at a time. But what happens if you have a saturated enough solution is once those crystals start, they will actually just start picking up other sugar molecules from the solution, stacking themselves into perfect crystals. And this happens for a lot of things. So after a certain point, you don't have to do anything. But this was a very distinct visual that I remembered and was able to find. All right. Cool. All right, so not only can we have liquids dissolved in solids, but we can also dissolve, sorry, get the Zoom meeting here. You can also dissolve gases in liquids. And this is how we get carbonated drinks of any kind, is that there are dissolved gases. Especially with sodas, but like lake water and seawater contains dissolved oxygen, which is what the fish actually need to breathe. And then our blood contains dissolved nitrogen, oxygen, and carbon dioxide. The carbon dioxide actually is what keeps, we haven't talked about pH yet, but we'll get there. And then tap water contains dissolved atmospheric gases too. Sometimes it contains a lot. That's why if you, especially if you go over to somebody else's house and you pour some tap water, and it's super cloudy when it first pours, but then it clears up. That's those dissolved gases coming out and not like, I don't know, other stuff. So the solubility of gases and liquids, so remember, as temperature increases for solids and liquids, the solids get more soluble. So if we have a, oops, solid and liquid, as temp increases, solubility increases. For gases and liquids, it's the opposite. As the temperature decreases, solubility increases. This is why a warm soda fizzes more and is like, well, depends on what you like, but I think a warm soda is less pleasant to drink than a cold soda because that carbonation comes out a lot faster. And also when you pour it, you're going to see that come out as well. The way that I remember how this goes is that for a solid dissolving in a liquid, as it gets warmer, it's getting closer to being a liquid. And for a gas dissolving in a liquid, as it gets colder, the gas is getting closer to being a liquid. And so the closer that they get to being like liquids, the more they are soluble. We're not going to mention Henry's law again, but so the solubility of a gas depends on pressure, which is Henry's law. So again, this is going back to before spring break, which I know is a different era altogether. But pressure is also related to the concentration of that particle. So in this case, the gas particles. So if we increase the gas, that means that there is more of those gas particles trying to dissolve into the liquid. It's kind of like increasing the pressure of a gas is kind of like adding more solid to a solution. Right, so if you add more salt to salt water, you're going to get more salt dissolved in the water. If you add more pressure of gas above a liquid, you're going to get more of that gas dissolved into the liquid. Which is why soda cans are at such high pressure and why they pop and hiss when you open them, because that high pressure helps keep the CO2 in the solution. There are other reasons that soda cans are pressurized, but you can look those up. So as soon as you open it up, especially if you've shaken the can and you've disturbed it a lot, when you release that pressure, that CO2 is going to try and come out of the solution. So if you really want a soda to explode in somebody's face, you would shake up a warm soda and then give it to them. Okay. So that's most of the concepts that we're going to talk about with solutions. And now we'll start getting into more of the math and the actual numbers that we use to talk about solubility beyond grams of solute in grams of water. So mass percent is different from our grams of solute per 100 grams of water. Because when we were talking about that, that was just 100 grams of water. Mass percent is 100 grams of solution. And the solution is the solute plus the solvent. So that's why we have mass percent here is mass of solute plus mass of solvent. Excuse me. So the example given here, if we have a solution with a concentration of 14% by mass, that's 14 grams of solute per 100 grams of solution. So these mass percents are actually very convenient to use. So we're going to have to call out another old thing that we learned, and that's density. Will get used in a lot of these problems. So calculate the mass percent. This is what we're trying to look for, is the mass percent of a sucrose solution containing 11.3 grams of sucrose and 412.1 milliliters of water. So if you remember, we can take milliliters, which is a volume, so 412.1 milliliters of H2O, and we can use the density of water to convert it from volume to mass. So here we want the mass of it, so it's going to be grams, so 1.00 grams of H2O has a volume of 1 milliliter H2O. So our milliliters of H2O cancels out, and this will just be 412.1 grams of H2O. And then our equation for mass percent is the mass of the solute divided by the mass of the solute plus the mass of the solvent and times 100. So we'll have our solute here. Remember, solute is the thing being dissolved in the solution. That'll be 11.3 grams of sucrose divided by 412.1 grams. Well, I guess, let me put these in the same order, sorry. This will be 11.3 grams plus the 412.1 grams of water that we have. So 11.3 divided by, and you have to use parentheses on your calculator. You can't just type 11.3 divided by 11.3 plus 412.1. You have to do 11.3 divided by parentheses 11.3 plus 412.1, and then close those parentheses, and then multiply by 100 will be 2.67% sucrose. So the total solution, the total mass of the solution, 2.67% of that comes from the sugar, or the sucrose. You can also use this to go the other way and figure out how many grams of sucrose are in there using the percent mass. So there are some other units. We won't use them very much here, but it's important to mention them. Parts per 100, right? So that's how many things out of the 100 are whatever your solute is. It's the same as percent. So that's what we just calculated. So this is 2.67%. It's also 2.67 parts per 100. We also have parts per million. So that would be, however many parts of a million parts are your solute. And then parts per billion. Especially for, you can look up around here even, you can look up the Reedley municipal water supply and what they've tested it at and get different quantities of things dissolved in it in parts per million or parts per billion. There's also parts per trillion. And I think PFAS, which is polyfluorinated organic solids, is supposed to be less than 6 parts per trillion or something. So you can look those up. It's publicly available information. And these are the units that they'll be using to tell you how much is in your water that you're drinking. So we can use this mass percent as a conversion factor between mass of the solute and mass of the solution. And the key to using mass percent, like any of the things that we've used that are percents, is you write it as a fraction. So, for example, one of the easy ways to do this is you can write it as the number of grams of solute per 100 grams of solution. So for our sugar solution from before, right? The mass percent of that was 2.67%. That's going to be 2.67 grams of the solute, which was sucrose, divided by 100 grams of the solution. So if you change your conversion factor, change your mass percent, if you want to use it as a conversion factor, you can convert it this way. Or you can just take the 2.67% and divide it by 100 and use the proportion rather than the percent. For example, how much sucrose in grams is contained in 355 milliliters, which is a 12-ounce soda, containing 11.5% sucrose. And this is 11% by mass. Assume a density of 1.04 grams per milliliter. So if we have, again, 355 milliliters of soft drink, soda, we first need, before we can use percent mass, we need to convert that volume into a mass. So it's 355 times 1.04 grams per 1 milliliter. So I'm just using the density. And then our milliliters cancel. So we get 355 times 1.04. That'll be 369.2 grams of our soda. And now if we want to know the amount of sucrose, we can convert this 11.5% into 11.5 grams of sucrose per 100 grams of solution. So we take our 369.2, multiply by 11.5, and then divide by 100. It gives us 42.5 grams of sucrose. So mass percent is just a conversion factor for the mass of the solute in the mass of the solution. Any questions? That's mass percent. The other one that we're going to use, so mass percent gets used a lot. Molarity, we will also use a lot. We'll talk about one other unit, molality, which I have a hard time saying. But molarity is the one that we're going to use the most out of all of them. And I would encourage you on every assignment, every exam, every question that's going to use molarity, just rewrite it as molarity equals moles of solute per liters of solution. Because it's very easy to forget that this is, again, another conversion factor between, instead of massive solute, massive solution, now we're talking moles of solute per liters of solution. So if you wanted to make a solution of a particular molarity or concentration, you usually put the solute in a flask first and then add water till you get the desired volume of solution. I don't think you're actually going to have to do this in lab at all. So if we have a flask and we want to make a 1 molar, again, molar is the same as molarity. Write that more clearly. Whoops. Molarity. And molarity equals moles per liter. So to make a 1 molar solution, you add 1 mole of sodium chloride. So you would weigh out 58.44 grams, that's 1 mole. And then you add it to your flask. Then you add water until it's dissolved, and then you mix it. And then you add water until it's full. And these are a special type of flask. So there's a line here. It's a volumetric flask. So this would be a 1 liter volumetric flask. And when you fill it up to that line, it would be like 1.0000 liters exactly. So they're made for weighing out or measuring out just a very, very specific volume. So if we wanted to calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting that to 2.5 liters, you have 55.8 grams of sodium nitrate, and we have 2.50 liters. Remember again, molarity is moles per liter. And that's both the definition and the equation for how you find molarity. So how do we get the moles of sodium nitrate?
Molar mass?
Yeah. Yep. Use the molar mass. So pull up this periodic table that has the masses. Sodium is 22.990. So sodium 22.99. Nitrogen, you can see it on there. We're going to use 14.01. Oxygen, we'll use 16.00. And then there's 3 oxygens, so we'll multiply that by 3. There's 1 of each of these. Oh, sorry. There it is. So 22.99 plus 14.01 plus 16. Oops. Sorry, 16 times 3. So the molar mass is going to be, so we have 55.8 grams, and we want to get moles. So the molar mass is always 1 mole, and the mass of that 1 mole is 85.00 grams sodium nitrate. So 55.8 divided by 85 is going to be 0.65 moles. And then we just take moles and we divide it by liters. So take that number, divide it by 2.5, and this would be a 0.3 sig figs, 0.263, capital M is molar. And we should probably include here that that's 0.263 molar sodium nitrate. So molarity is a new unit, but it is a fairly simple unit. It's just moles divided by liters. So if I asked you, okay, you have a 0.263 molar solution of sodium nitrate, how many moles are in 1 liter? Molarity is moles per 1 liter. So if it's 0.263 molar, how many moles are in 1 liter? No math required. 0.263. There's 1 liter. So yeah, in 1 liter you would have, thank you for answering, the brave soul. So in 1 liter of a 0.263 molar, this is 0.263 moles of NaNO3 per 1 liter of solution. So if you had 2 liters, you just multiply 0.263 times 2. Okay. So we can use molarity as a conversion factor between moles of solute and liters of solution. So how many grams, right, so we can take this the other way. If we have a 1.95 liters of a 0.781 molar sucrose solution, how many grams of sucrose are in there? Most of the time, I will tell you this, most of the time your equations will not start with molarity. That's because we almost always use molarity as a conversion factor. So you usually start with the number that's not a conversion factor. So in this case, that's 1.95 liters. So if we have 1.95 liters of solution, and again, molarity, capital M, equals moles per liter. So this 0.781 molar, we can multiply that. 0.781 moles of sucrose divided by 1 liter of solution. So 1.95 times 0.781 will be 1.52 moles of sucrose. And once we have the moles of sucrose, we could use that to find how many grams of sucrose there are, because we can calculate the molar mass for sucrose. I'm not going to do that right now, though. Okay, so this is another way that these questions can be worded. Actually, let me pause for a beat. Are there any questions about this in general? You can go home, you can think about it. I will be here early again on Wednesday. You ask me more questions then. Questions about anything, doesn't have to be about this. So if there's no questions there, we'll move on to this. This is another way these questions can be worded. How many liters of a 0.225 molar potassium chloride solution contains 55.8 grams of potassium chloride? So again, molarity. There's a capital M, could also be molar. Same thing, is moles per liter. So it's our conversion factor between moles and liters. So if we have a number of moles, we could calculate how many liters would contain that number of moles. So we can calculate, because we have a mass of potassium chloride, we can calculate how many moles that is. So 55.8 grams KCl. We'll need the mass of potassium and chlorine. Chlorine is 35.45. And potassium is 39 point, oh, it's backwards on here. Wait. Mirrored. 39.098. And there's one of each of those. So we can just add those together. So the molarity of potassium chloride is going to be 8. That's grams per mole. So if we want the moles, we're going to multiply by 1 mole and divide by 74.548 grams. That's grams of KCl, and this is moles of KCl. So 55.8 divided by 74 gives us 0.7485 moles of KCl. And then if I rewrite, so 0.225 molar KCl is the same as 0.225 moles of KCl divided by 1 liter of that solution. So how do I multiply by this 0.225 per 1 liter to get liters?
Trying to get liters by itself, correct?
Mm-hmm.
So can't you, so since it's division, you're gonna do the opposite, so you're gonna multiply, right? 0.225 from that side and then to the other side, right? To cancel it out.
Oh, I see what you're saying. So I was just saying that these are both the same. Yeah. So these are both the same, right? This molar just means that it's this.
Okay.
So I need to put this into here. So which do I put on top? Yeah. So we want that 1 liter because we want liters of solution. And 0.225 moles of KCl on the bottom. Because then we'll get moles of KCl to cancel and just leave us with liters of solution. So that's 0.7485 divided by 0.225. So it would be 3.33 liters of solution. So 3.33 liters of solution would contain 55.8 grams of potassium chloride. I feel like this could be a lab. I feel like it should be a lab. Yeah, it's one of those things could be nice and tangible. All right. Any questions? Yeah.
I have a question on the where it says 0.225 mKCl. So we converted that to molarity. That's molarity, right?
So this is molarity.
Because it's moles over the solution.
Mm-hmm.
So then we used the did we just use the moles? When we did the 0.7485 times the 1 liter over the moles. So we just used moles, right? We didn't use molarity.
We used molarity.
We did.
Yeah, so
molarity.
we just took the molarity. So we took the molarity and said, okay, this capital M is actually a compound unit. That means that it's this many moles over 1 liter. So that's why I wrote it out this way. And that's why I say to write this out every time, because this is not so clear that it's a conversion factor, in my mind at least. If you can write it out like this, then you can see, oh yeah, this relates the amount of moles to the number of liters of solution. And so then we just had to take this and flip it to use it to get rid of moles to find the number of liters.
Got it.
Yeah. All right.
No, I had a question too.
Oh, yeah.
So 1 liter over 0.225, you're always going to use that to convert, right? You're just going to flip it?
You'll flip it. Well, you'll flip it if you need to flip it.
But if you don't need to flip it, you don't have to.
You don't have to flip it. So this is just like any of the other conversion factors we had.
You only did it to cross out moles, right?
Yeah. So here we want to cancel moles. So we need to flip it so that moles was on the bottom because we have moles here. So it cancels out because what we want is liters of solution because their question.
Liters on the left side, we would put liters on the bottom and moles on top to cancel out liters, right?
Yes. Yes.
Sorry, I'm just making.
No, it's okay. Yeah, I had to. Yeah, I'm following. Yeah, if this instead was like we had liters of solution and we wanted to find moles, then we wouldn't flip it. Yes. Good. I think we're going to leave off with that. Just over halfway. Okay.